As we mentioned in the introductory video to this series, quantum computers are devices that exploit quantum mechanical effects to speed up certain computational tasks. Now, similar to classical systems, which have a fundamental unit of information that we've been calling the bit, quantum devices rely on a fundamental unit, which we call the quantum bit, or the qubit for short. Now, qubits are special because they exhibit quantum properties like superposition and entanglement, which are the effects we want to exploit when performing quantum computations. There are many different ways in which we can introduce the concept of a qubit, but to me, the most natural explanation is by way of example, where we use a physical system like the spin of an electron that does indeed behave like a qubit. So for the next few videos, we're going to stick with this approach and then gradually move towards the more abstract representation of qubits and the quantum operations that we will use to implement all the different protocols and algorithms. So one of the fundamental properties that particles like electrons have is something called spin. And because electrons are charged particles, this spin manifests itself in the form of a magnetic field. So to test what the spin of an electron is, one can perform what is known as a Stern-Gerlach experiment. So the Stern-Gerlach experiment is implemented by the use of two magnetic poles, a north pole and a south pole, where each of these poles is shaped in a way so that the magnetic field between them is non-uniform. So what this means is that there's a higher concentration of magnetic field lines at the top, which means that the field is increasing along the positive z direction. Now, if one were to take an object with an intrinsic magnetic field, like let's say a small bar magnet, and send it through this apparatus, what one will see is that the magnet will deflect upwards if its magnetic north is pointing in the positive z direction. On the other hand, if its north is pointing in the minus z direction, well, we will see that magnet deflecting downwards. And that is because the non-uniform magnetic field generates a force that causes a tiny bar magnet to deflect. Now, if the bar magnet is oriented with its magnetic field in the x direction, well, if this apparatus is designed correctly, so that the force exerted when the magnet was pointing up and when the magnet was pointing down is equal, then in this particular case, that magnet should travel in a straight line and end up right in the middle of this screen. More generally, if one were to align the magnet at an angle theta with respect to the z-axis, what we will see is that the bar magnet will deflect at different heights that are proportional to that angle theta. So for theta equal to 0, we will get the same as what we had for the magnet pointing in the north direction, so that gets the largest deflection in the positive z direction. For theta equal to pi, we get the minimum, and for theta equal to pi over 2, which was the one where we had the magnet in the x direction, then in that case the magnet will just travel straight, but anywhere in between the magnet will deflect at some height that is proportional to that angle. So the next question is, what will we observe if we replace this tiny bar magnet with an electron? So in principle, we should see the exact same behavior, since electrons have a magnetic moment generated by its intrinsic spin, as we mentioned. Now, unsurprisingly, if the spin of this electron is pointing in the positive z direction, well, we see exactly the same as we see for the bar magnet. The electron deflects upwards. Similarly, if the spin of the electron is pointing in the minus z direction, well, we see it deflect downwards. But here's where things get really interesting. If now we take the electron spin and point it in the positive x direction, unlike what we see for the tiny bar magnet, where it travels in a straight path, what the electron does is, in 50% of the experiments we run, we see the electron deflecting upwards, and for the remaining 50% of the experiments, we see it deflecting downwards. And more generally, if we have the electron with a spin pointing at an angle theta with respect to the positive z-axis, what we see is that the electron always deflects either upwards or downwards with a probability that is proportional to that angle theta. But what's surprising is that we never see the electron deflecting at any other height other than what we observe for when it's pointing up or when it's pointing down, which is very different to what we observe with a classical tiny bar magnet. Now, the reason why electrons show this probabilistic behavior is partially related to what is perhaps the most debated question in all quantum mechanics, which is the measurement problem. Now, even though this is a very interesting subject, we will not be discussing it, at least not in the immediate future. We will simply use this as empirical evidence for how electrons behave when we perform measurements to detect their spin. Now, what we want to do next is try to build a model for the electron spin. So one thing we might be tempted to do is to assign to it a probability vector like the one we discussed in the previous video. So we could say that the way we describe the electron spin is with a vector S, where the first component is the probability of measuring the electron deflecting upwards, and the second component is the probability of the electron deflecting downwards. And at first glance, this seems to work, right? For the case where we had an electron with a spin pointing in the plus z direction, well, the vector that described that electron was given by 1, 0, right? Because the observations of performing that experiment over and over again was that we were always seeing the electron deflecting upwards with probability of 1 and never deflecting downwards, so a probability of 0. Similarly, for an electron with a spin pointing in the minus z direction, we could ascribe the vector 0, 1, where again the probability of measuring it deflecting upwards is 0, and the probability of seeing it deflect downwards is 1. Now let's consider the case we have here where the electron is pointing in the plus x direction. Well, since we observe that electron deflecting upwards and downwards, each with 50% probability, well, we could assign a vector where we have probabilities of 1/2 and 1/2. Now, the issue with doing this is that if we were now to perform an experiment where the electron has a spin pointing in the minus x direction, well, we will also observe that the probability of it deflecting upwards or downwards is 50% each. So the vector representing that particular electron would also be of the form 1/2 and 1/2, which says that these two electron spins are virtually indistinguishable from each other. And the problem with this is that this can't be right, because there's another experiment that can show us that an electron with a spin in the plus x direction and an electron with spin in the minus x direction are different. And the way to show that is by taking our Stern-Gerlach apparatus and rotating it at 90 degrees. So if we now have an electron with spin in the plus x direction, well, by symmetry, what we observed is exactly the same as what we had when the apparatus had the magnetic field in the plus z direction and the spin was in the plus z direction. So we see with 100% probability this electron deflecting in the plus x direction. Similarly, if we now have a spin pointing in the minus x direction, well, we see that electron always deflecting in the minus x direction, which tells us that if we want to assign a vector to represent electron spin, we can't just do it using the probability vectors that we discussed before. Furthermore, we can show that mathematically this just doesn't work. So for example, if we take again our vector for spin in the plus x direction, which we said was a vector with 1/2 and 1/2, well, we can actually factorize out this 1/2 and express this in terms of the vector 1, 0 and the vector 0, 1. So if we add up these two vectors, we see that we get the same as we have here, which means that an electron with spin in the plus x direction can be expressed in terms of the vectors for electrons with spin in the plus z direction and in the minus z direction. But then by symmetry, if we take the experiment where we have rotated the Stern-Gerlach apparatus, and then we use a particle with spin in the plus z direction, well, we should see the exact same thing we saw when this was rotated 90 degrees, which is that with 50% probability, that electron should deflect to the left, and with 50% probability, it should deflect to the right. Which implies that then, just like we had here before, where we could express the spin of an electron in the plus x direction as a sum of spins in the plus and minus z directions, we should be able to then express this spin, which is in the plus z direction, as the same type of sum of vectors in the plus x and minus x direction. But here's the problem. If we now replace this with a column vector representation, we said that for the plus x it was 1/2 and 1/2. And from observations, we also had that for minus x was 1/2 and 1/2. Well, what we get here is a vector of the form 1/2 and 1/2, which was not originally what we had defined the vector for spin in the plus z direction to be. If you recall, we had defined this to be the vector 1, 0. So mathematically, when we try to express these vectors in a way that describes observations for this particular experiment, we don't get a consistent representation of what we had defined for the spin of an electron in the plus z direction to be. So the question now is, how do we move forward? Clearly, this model of using probabilities to explain the behavior of the spin of electrons doesn't work. And this problem mainly stems from the fact that we need to find an expression that when we add the vectors that describe spin in the plus x direction and minus x direction, can help us recover the expression for the spin in the plus z direction. But here's the problem. Our definition of spin in the plus z direction is given by the vector 1, 0. And we need two elements, let's say a vector with components a0, a1, and another vector with components b0 and b1, that when added together give us a 1 on the top entry and a 0 in the bottom entry. Well, the main issue here is that for the bottom entry to be 0, there are no positive numbers that when added together will give us 0. The reason this need to be positive numbers is because we are saying that these elements are probabilities. So how do we get around this issue? Well, a solution would be to, instead of defining a probability vector that we're calling S, with the probability of measuring the electron deflecting in the positive z or the negative z direction, is to instead define a vector with some components, let's call them S0 and S1, where we relax the restriction of S0 and S1 having to be probabilities, so they can take also negative values. Now, to make this consistent with the probabilistic observations that we have from the Stern-Gerlach experiment, what we can do is we can say, okay, well, the probability of measuring an electron deflecting in the plus z direction is equal to S0 squared, and the probability of measuring deflecting in the minus z direction is S1 squared. So in general, this vector S with components S0 and S1, where this S sub i's are real numbers, but also meet the condition that when we add together their values squared, they must be equal to 1, because these represent probabilities. Now let's compare this with the definition we had for our bit, which we said was a vector with components beta 0 and beta 1, where this beta sub i's were either 0 and 1, and where the length of the vector, which was given by beta 0 squared plus beta 1 squared, and then the square root of that had to be equal to 1. Now, because 1 squared is equal to 1, we can actually use this same restriction for the definition of the vector that describes our spin. So here we can see that these two are very similar to each other, but where in the case of the bit, the vector values could only be 0 or 1, and in the case of this spin vector, the values of S0 and S1 are real numbers, that when we square them and add them together, they must be equal to 1. So now let's see if this definition is consistent with the observations from the Stern-Gerlach experiment. So let's say that for spin in the plus z direction, we have the vector 1, 0. So that means that the probability of measuring spin in the plus z direction, which is given by s0 squared, which is 1 squared, is equal to 1. So this is exactly what we observed. And similarly, for the probability in the minus z direction, we have s1 squared, which is 0 squared, which is equal to 0. We can do the same thing for spin in the minus z direction, which was 0, 1. And we can show that the probabilities correspond to 0 and 1. Now let's look at the more interesting example of spin in the plus x direction. So in that particular case, we have that the observed probability of measuring the spin deflecting in the plus z direction is 1/2, and the probability of it deflecting in the minus z direction is also 1/2. So what values should we pick for the components s0 and s1? Well, since these are equal to s0 squared and s1 squared, we could simply pick the positive square root of the corresponding probabilities, which would be the square root of 1/2. And we do the same thing for s1. So we could say that the vector corresponding to the spin of an electron in the plus x direction is given by the square root of 1/2 and the square root of 1/2 for each of the elements. And let's recall that we can then express this in terms of the spin along the plus z and minus z directions, right? We can say that this is equivalent to the square root of 1/2 times the vector 1, 0 plus the square root of 1/2 times the vector 0, 1, which is equal to, I'm going to rewrite this as 1 over square root of 2 of the spin in the plus z direction plus 1 over root 2, the spin in the minus z direction. And then we said that by symmetry, we should be able to express the spin along the plus z direction as the sum of 1 over square root of 2 of the spin in the plus x direction plus 1 over square root of 2, the spin in the minus x direction. So with this, we can then find out what the vector for the spin in the minus x direction should be. So we know that this is the vector 1, 0. This is 1 over root 2 of the vector 1 over root 2 and 1 over root 2 plus 1 over root 2. And then we can represent this in terms of some arbitrary variables s0 and s1. And then we can just solve for s0 and s1. So here we have that s0 must be equal to root 2 over 2, which is actually the same as 1 over root 2. And s1 should be minus root 2 over 2, which is minus 1 over square root of 2. So the vector that represents the spin in the minus x direction is given by 1 over root 2 and minus 1 over root 2. And we can see that this is consistent with the probabilities that we see from observations when we perform the experiment using the Stern-Gerlach apparatus, right? Because we said that the probability of measuring spin in the plus z direction is going to be equal to s0 squared, which in this case is 1 over root 2 squared, which is 1/2. And the probability of measuring the spin in the minus z direction is s1 squared, which is minus 1 over square root of 2 squared, which is also 1/2. So what we can do now is say, okay, well, I'm going to say that a possible physical implementation of a qubit is by the use of the spin of an electron. And I'm going to associate with a qubit value of 0 what I have for the spin of an electron in the plus c direction, and with a 1, the spin of an electron in the minus c direction, which is consistent with the column vector representation we had given to a classical bit. But now we can say that we also have some special elements, which we call the plus vector, representing the spin of an electrode in the plus x direction, which is given by a vector with elements of 1 over square root of 2 and 1 over square root of 2, which is equal to the sum of 1 over root 2, 0, plus 1 over root 2, 1. So recall, this is spin in the plus z direction, and this is spin in the minus z direction. And we call this type of element a superposition. Similarly, for the spin in the minus x direction, we associate a vector that we call minus with elements 1 over root 2 and minus 1 over root 2. So it's also a superposition of the form 1 over root 2, 0 minus 1 over root 2, 1. So we see that qubits are elements just like bits that take values of 0 and 1, but can also be in this special state called a superposition, which is a linear combination of being in state 0 or being in state 1. Now, more precisely, the real definition of a qubit, let's call it a vector Q with elements alpha 0 and alpha 1, really says that these components, alpha sub I, are complex numbers where the sum of their norm squared must be equal to 1. And, we could do square root here if we want to define it in terms of the length of this vector. But so far, we've only shown this for real numbers, not complex numbers. But in a future video, we'll show step by step why these components must be complex. So let's now go to Python and show how we can simulate this type of elements by using Qiskit. Now, technically, we could do something similar to what we did in the previous video and define these vectors using NumPy arrays and then creating a rule where we take the square of those elements to find probabilities. But luckily for us, Qiskit already has a module with different classes that allows us to make this process a lot simpler. So what we're going to do is import NumPy, and from Qiskit quantum info, we're going to import the state vector class. So with the state vector class, we can do something as simple as saying I'm going to define our ket 0 as a state vector that takes a list with the elements that I want for that vector. And then if I display that, this is going to show me the ket representation of that vector. Now the nice thing is that this object has some methods that allow me to get valuable information about the state vector itself. So for example, I could use the probabilities method to extract the probabilities of measuring 0 and 1. Now, because I have ket 0, what I'm going to get is an array that tells me that the probability of measuring 0 is 1 and the probability of measuring 1 is 0. Now, I could also define, let's say, the ket plus by doing state vector and passing a list that, as we said, consists of the elements square root of 1 over 2 and square root of 1 over 2. And if I display that, I can see now that superposition state of 0 and 1 with coefficients of root 2 over 2. And if I try to extract the probabilities, I should get a half for 0 and a half for 1. Now, I could also display this state in vector notation by using the draw method. And if I only pass here this option LaTeX, I'm going to, by default, get the same output, which is the ket representation. But if I also pass here the parameter convention and specify it to be vector, what I get is a row vector that corresponds to state plus. So that's one of the things to keep in mind with Qiskit, that these vectors are displayed in row format even though they're supposed to represent column vectors. Now, another way to define these vectors is, for example, let's define the ket minus using, again, the state vector class. But now I'm going to use this method from label, and I can just pass a minus sign here, and that should give me the ket representation of state minus, for which I can also find, for example, the probabilities. Or I can also, for example, sample the state to get a certain number of counts, as if we were performing measurements, like in the Stern-Gerlach apparatus, where we run several experiments. So let's say I want to run 50 experiments. So ideally, in 25 of these experiments, I should see state 0 and in the other 25 of the experiments I should see state 1, but obviously this is probabilistic, so I'm not going to get exactly 25 and 25, but it should be close to that. So here I get 23 of those experiments were 0 and 27 were 1. So these are some of the different ways in which we can represent qubits in Qiskit. Now in the next video, what we will see is how to take a state vector, which represents a qubit, and evolve it through quantum gates, just like we did for bits and p-bits, to get a different state vector that we desire at the output. Thanks again for watching, and I'll see you in the next one.